In this video, we are going to be looking at some thermodynamics problems. So I got a couple here from your textbook. So the first one says the temperature of a rigid, constant volume sealed container of gas increases from 100 Celsius to 200 Celsius. The gas pressure increases by a factor of. So again, this is a sealed container. That means that the volume of the container doesn't change. So volume is going to be constant. We're dealing with a gas, an ideal gas, and we know that the temperature is changing. So we'd like to know by how much the pressure is going to change, the ratio between the final pressure and the initial pressure. So first thing that we want to do is, of course, write the equation for an ideal gas, which relates pressure, volume, and temperature with the number of moles, N, and the universal gas constant, which is R. So if we write it for the first or the initial temperature, we'll have that the first or initial pressure times the initial volume equals NR initial temperature. Nobody said that the number of moles was going to change. In fact, this is a sealed container, so the N is the same. The volumes are going to be also the same. What's going to be different are the pressures and the temperatures. So looking at this equation, we could notice that the volumes are the same and the N and R are constants. So we could divide one equation by the other one. So dividing the left-hand side, so P1 V1 divided by P2 V2, that should be equal to nRT1 divided by nRT2. This is a well-known method for solving equations. Whenever you have two equations, you can divide the left-hand side of each equation and then make it equal to the division of the right-hand side. So in this case, that will work very nicely because then we get the N and the R canceling, and also the volumes are going to cancel because they're equal. The volume here is constant. So we get P1 over P2 equals T1 over T2. So solving for P2, the final pressure, P2 equals P1 times T2 divided by T1. So we want to find out the ratio between P2 and P1. So all we need to do now is replace the temperatures. Now here you have to be very careful because PV equals nRT only works if you're dealing with temperature in Kelvin, not in Celsius. So we need to calculate what's the T1 temperature in Kelvin. So T1 is 100 Celsius, so that becomes 373 Kelvin. T2 is 200 Celsius, so that becomes 473 Kelvin. And now once the temperatures are in Kelvin, we can replace, and P2 will be equal to P1 multiplied by a number which is 473 divided by 373. That number is around 1.3. So the final pressure is 1.3 times the initial pressure. So the pressure increases by a factor of 1.3. So the answer is B. All right. Let's move on to the next one, example 18.5. It says that we have a cylinder of gas at 0 Celsius and a piston compresses the gas to half of its original volume and 3 times its original pressure. What is the final gas temperature? So again, this is a problem dealing with an ideal gas. So the equation PV equals nRT is going to be what we need to use. Again, we got to be careful with the temperatures. Make sure that they are in Kelvin. So the initial temperature is 0 Celsius, so that gives us 273 Kelvin. The volume, the final volume, it says that the piston compresses the gas to half of its original volume. So the final volume, or V2, is equal to 1/2 of the initial volume that I'm calling V1. The problem, the next sentence says that, or the next part of that sentence says that the pressure is 3 times the original pressure. So the final pressure, P2, is 3 times P1. We're looking for the temperature, the final temperature, knowing that the initial temperature is 273. The number of moles is equal. Nobody said that any gas was allowed to come out of the piston, of the cylinder. So the number of moles is going to be the same, N1 equals N2. So from PV equals nRT, if we divide by the temperature on both sides, we know that when the number of moles in a gas doesn't change, PV divided by the temperature should be constant, should be the same. So we can write P1 V1 over T1 equals P2 V2 over T2. And solving for T2, remember that we're looking for the final gas temperature. So we're going to solve for T2. That's the equation that you have right there. So T2 equals T1 P2 over P1 times V2 over V1. Just a little bit of algebra from the line that I wrote before that one. And all you have to do is replace now. So T2 equals T1. T1 is 273. The ratio P2 over P1 comes from here. Comes from here. P2 over P1 is 3 times, so we write a factor of 3. And the ratio V2 over V1 gets from here. V2 divided by V1 is 1/2. So that's the number here. Factor of 3 from the pressure was put in there. And that gives you T2 equals 273 times 3 times 1/2. The answer is 409 kelvins. Jumped the gun there. So the final answer is 409.5 kelvins. And since they gave us the initial temperature in Celsius, we should be courteous enough to give the answer in Celsius also. So we need to convert 409.5 Kelvin to Celsius. To do that, you subtract 273. So 409.5 minus 273 gives you the final answer, which is 136.5 Celsius. So the gas starts at 0 Celsius, it ends at 136.5 Celsius. All right, so another application, another problem where we're just applying the ideal gas law, PV equals nRT. All right, let's take a look at another problem. So in this problem, let's read it before I do all the drawing here. It says that we have a gas at 2 atmospheres of temperature, ATM atmospheres, and a temperature of 200 Celsius. And it is first, we allow this gas to expand isothermally until its volume has doubled. It then undergoes an isobaric compression until it returns to its original volume. So we let it expand and then we compress it. And they want us to first show the process on a PV diagram. And then we need to calculate the final temperature of this gas. Final temperature and pressure. All right, so let's start with the diagram. So we're doing a P pressure versus volume diagram. So a process happening in a gas to a gas can be represented in the PV diagram as a, so at any moment a gas, an ideal gas, will have a specific value of pressure, volume, and temperature. Now, since the pressure, the volume, and the temperature are related to each other, we basically, if we know the pressure and the volume, we also know the temperature, because pressure times volume is nRT. So the state of the gas, those three variables, pressure, temperature, and volume, they represent the present state of a gas, how much pressure it has, what's the temperature, what's its volume. But only two numbers out of those three, two numbers are enough to figure out everything you want, because the temperature, as I said, if you know the pressure and the volume, you easily find the temperature. So the state of a gas is represented as a point in a PV diagram. At any given moment in time, a gas is represented by a dot somewhere in that PV diagram. As we do things to a gas, as we allow the gas to expand and so on, the gas describes a trajectory on a PV diagram. Depending on what we're doing with that gas, we could represent that as a curve that moves around in the PV diagram. At any given moment, the gas has a particular pressure and it has a particular volume, and with PV equals nRT, you can find what is the particular temperature of the gas at that particular point. So that's the idea of a PV diagram. Okay, so long digression here. Before we show isothermally, what does a isothermal process look like in a PV diagram? So this was discussed in some of the videos. I'm putting some information here that we know that the original or the initial point where we start in this journey, we starting at 2 atmospheres, 2 ATMs. We start in a particular volume that I call in V1 or V initial. No, I call V initial the volume, V initial. and we started at an initial temperature of 200 Celsius. Now the gas is going to move down a red curve like the one you see. As the gas expands isothermally, it follows a particular curve. That curve is not difficult to figure out because since PV equals nRT, and isothermal means that the temperature remains constant as the gas is expanding, we know that the pressure of that expanding gas is going to go like nRT divided by volume. So as the volume goes up, the pressure goes down. And the particular curve that we have is a hyperbola. That is the kind of curve that you've studied before in math, is like a constant divided by x. So that's a curve that goes down. As x increases, y goes down. So as the volume increases, the pressure goes down. So that is a hyperbola curve. The isothermal is a hyperbola. So I draw that as a red curve there. And it says that the gas is going to expand isothermally until its volume has doubled. So our final point here has a volume of 2 times the initial, right here, 2 times the initial volume. That's the initial volume. We're stopping the expansion after at a volume equals to 2 times the initial volume. All right, so we have graphed the process all the way to here until the volume has doubled. Then it says it then undergoes an isobaric compression. Isobaric compression means constant pressure. So if we're going to move on the PV diagram at constant pressure, we're going to need to move horizontally. And we're going to be going in a particular direction. That is this direction. First, we expand it isothermally, and now we're being compressed. The gas is being compressed isobarically. So we're keeping the same pressure. So the pressure is constant, so we move horizontally in the PV diagram, and we're going to go until we go to the original volume. So the compression happens from this point to this point when we have reached the original volume. So those are the two processes happening here, and so that's represented in a PV diagram. So we did the first part of the question already, and now they want us to calculate the final temperature. So the temperature right there, and to calculate the final pressure also. So notice that we have a bunch of information here. Let's start with one. So at this point, we know that the temperature is still 200 Celsius, right? We know that because it's an isothermal. Isothermal means we're keeping the temperature the same. So that point that I'm calling point 2 has a temperature of also 200 Celsius. That point 2 has a pressure, which we're calling PF, and it has a volume of 2 VI. So if we did PV equals nRT for that point number 2 right here, we're looking at that point, we'll write PF times 2 VI equals nRT initial. Okay, so that's an equation we can write for using that point at the bottom. PF times 2 VI equals nRTI. TI is 200. I could replace that, but just leave it like that for a second. At this other point, the top at the beginning of the isothermal, we can write PV equals nRT also. So P is 2 ATMs. The volume, I'm just calling it VI, and the PV equals nRT initial. Now notice that the right hand side of that equation is the same, is nRT initial for both points. So we can do 2 atmospheres V initial equals P final times 2 V initial. So P final times 2 V initial is going to be equal to 2 atmospheres times V initial. Again, because notice the equal sign here, nRTI, notice the equal sign here equals nRTI, so they're the same. The right hand side of both equations is the same. So PF times 2V initial equals 2 atmospheres times V initial. Cancel V initial on both sides, and you get PF equals 1 atmosphere, because it's 2 atmospheres divided by 2. So we got part of the answer. We know now that the final pressure, the gas reaches a final pressure of 1 atmosphere. It went from 2 atmospheres to 1. So on the p-axis, I can put a 1. I know the PF, the final pressure is 1 atmosphere. Now, at that point, the 1, 2, 3 point, the final point, the one that we're calling final point, again, we're looking for the final temperature. So we're going to use the information we have to figure out that temperature. So at that point, PV equals nRT says P final, we already know that is 1 atmosphere, times the initial volume equals nR times the final temperature, which is what we're looking for. So let's replace P final. P final, we just figure out is 1 atmosphere, so 1 atmosphere times V initial equals nR T final. So we're looking for T final. The only thing that we're missing here is the initial volume. Also, I guess we don't know the N. But let's see what else we can do. So we have that equation that we have obtained by writing PV equals nRT at this point, that one at the bottom. Now I'm going to use the second point, the point above that one, which is the point with the 2 atmospheres and 200 Celsius. For that point, PV equals nRT says 2 atmospheres times V initial equals nR times 200 Celsius plus 273. Remember, we're writing the temperature in kelvins. So that is the equation for that point. This point right here, the one that is blinking in the screen, that is the point for which we wrote the equation 2 ATM times V initial equals nR factor of 200 plus 273. So notice that we have now 2 equations, both having nR and V initial, and we're looking for T final. So it looks like we could do something like we did in the previous problem and divide by one equation by the other. So divide the left-hand side, we get V initial is going to cancel, the nR is also going to cancel. The left-hand side says 1 over 2, that's 0.5. The right-hand side says T final divided by 473. So that gives us the final temperature in Kelvin will be 200. TF will be 0.5 times 273, which gives you 236.5 Kelvin. If you want the temperature in Celsius, and that's what they want that, they say want the final temperature in degrees Celsius, then we need to convert 236.5 converted to Kelvin converted to Celsius is subtract 273, and that gives you a negative temperature. So final temperature minus 36.5 Celsius. So the gas ends up quite a bit cold. Started at 200 Celsius, it ended up at minus 36.5 Celsius after these isothermal and the compression have been done to the gas. All right, let's take a look at this other one, at this multiple choice also from your textbook. So this one says that we're looking at a PV diagram again. The process is taking us from one point to another, and I already drew the picture, didn't have that, I just drew that. So the picture just gave us that process going from one point to another, and they're asking us what is the work done on the gas in this process. That on the gas is going to be important, but let's see. So the equation that tells us the work done when a gas expands or contracts is, in general, is going to be the integral of the pressure with the volume. When the pressure is constant, as in this example, that pressure times the change in volume is clearly the area. In general, the work done by the gas is going to be the integral of the pressure with respect to volume. In this simple example here, we have a constant pressure of 2000. So it's just simply the pressure times the change in volume. So 2000 pascals is the pressure, and we're going to multiply that. That's the MKS unit for pressure. The international system of units for pressure is Pascal. And so 2000 pascals times the change in volume, we can see that the gas went from 2 cubic meters to 4 cubic meters. So the change in volume is 2 cubic meters. Pascals times cubic meters will give you energy. This is work, so energy. So 2 times 2 is 4, 4,000, and pascals times cubic meter is a joule. So the work done by the gas is 4,000 joules. Now, what they're asking us is the work done on the gas. We calculated the work done by the gas, and we want the work done on the gas. These two works are the opposite or the negative of each other. If the gas does 4,000 joules of work on the environment, that is, the gas is doing a certain amount of work, the 4,000 joules is done by the gas on the environment. But if we want the work done by the environment on the gas, it will be the negative of that. That's simply because the motion, the force that is when the gas is expanding, the force of the gas pushing on the piston is making the piston go in the same direction as the force. So that gives you a positive amount of work. But from the point of view of the environment, the gas and the environment are in equilibrium, so the environment is pushing in the opposite direction. It's the atmosphere is on the other side of the piston that is moving. So it's applying a force to the piston in the direction opposite of the motion of the piston. That will give you negative work. So the work done on the gas is the negative of 4,000 joules. So the right answer is minus 4,000 joules. Again, this is because they said that they ask us about the work done on the gas by the environment. If the question had been, what's the work done by the gas on the environment, the answer will be 4,000. So careful with the wording. All right, so answer is D, minus 4,000 joules. Let's move on to the problem below that one. It says 3 possible processes A, B, and C take a gas from state I to state F. For which process is the magnitude of the work the largest? So 3 processes here going from the initial to the final. Process A takes us from the initial point, the initial state. We increase the pressure at constant volume. We reach a certain final pressure, and then we expand the gas at constant pressure until we get to F. That is process A. In process B, we started at the initial state of the gas, and we move through that diagonal, increasing at the same time the pressure and the volume until we reach the final point. In process C, we expanded the gas at constant pressure until we got to that corner, and then we stopped the expansion. We kept the volume of the gas constant, and we increased the pressure of the gas until we reach the final point. So those are the 3 processes. The question is, which of these 3 processes, or for which of these processes, 3, the magnitude of the work is the largest? The magnitude of the work is the largest. They're not saying the work done by the gas or the work done on the gas, because they're saying magnitude, so it wouldn't matter. It's a positive number. Either way you take it, we're looking at the magnitude, which is always a positive number. So let's think about it, the work done by the gas. So how do we do that? The work done by the gas, as we just said before, is going to be the integral of the pressure with respect to volume. So we're going to follow the curve that gives us the pressure as a function of the volume, the curve in the PV diagram. So remember that integral of a function with respect to a variable is the same as the area under the graph of the function. So for process A, we're looking at the work being the area under the graph, under the trajectory that takes us from I to F. So that area is the rectangle in blue that you see in the picture. That is the work done by process A, or I should say during process A. This is the work done by the gas. If we follow process B, the diagonal thing, we're looking at the area under that diagonal line. So that is the area of the trapezoid that you see in the picture in red. So that is the work done during process B. And finally, for process C, we're looking at that area. So clearly, looking at the picture, the process that has the biggest area, meaning the biggest amount of work, is process A. The expansion happened at a higher pressure, and that gives you a higher amount of work. All right, so the answer is A. All right, for the next problem, we have the same three processes that we just discussed, but now they're asking us something different. They're asking us for which process is the heat transfer the largest. Heat transfer the largest. So when a gas moves from some initial state to a final state and it follows a particular trajectory in the PV diagram, depending on the process, you might have to give heat to the gas. You might have to warm up the gas if you want to make it expand, or you might have to take heat away from the gas, so the Q will be negative, etc. You, depending on the process, you may or may not have to give the gas a certain amount of heat. But as the gas is doing whatever it's doing, the gas can also be doing work. If it's expanding, the gas will be doing positive work. So the first law of thermodynamics, which I just wrote there, says that the change in the internal energy of the gas is given by Q minus W. So W means the work done by the gas, so that W will be positive if the gas is expanding, and that W will be negative if the gas is being contracted. The delta U means the change in the internal energy of the gas. Now that internal energy of a gas, of an ideal gas, depends only on the temperature. It's a function of the temperature. So the change in internal energy for these processes is the same. All processes are taking the gas from the initial to the final point. At the initial state, you have a certain temperature. At the final point, you have a certain temperature, TF, and the change in energy, in internal energy of the gas for all processes is therefore exactly the same. All these paths will have the same change in internal energy. The internal energy only depends on the temperature of the gas. So in the equation delta U equals Q minus W, the left-hand side is the same for all paths. Delta U is the same, and it is equal to Q minus W. So if you solve for Q, because they're asking us about which one has the greatest heat transfer, so we're looking for the heat given to the system to make it go from the initial to the final state. So Q would be equal to delta U plus W. Since delta U is the same for all processes, A, B, and C have the same delta U because they all start and end at the same point, then the difference in Q will be given by the difference in work in W. So the biggest Q will be in the path that has the biggest amount of work done. And we already answered the question about which path has the biggest amount of work done. The previous question we argued that the biggest amount of work was done by path A, then B, path B had the next, and path C was the smallest amount of work. So clearly the one that has the biggest amount of heat transfer would be path A, or process A would be the right answer here. All right, that's all for now.